Yesterday we've started to talk about the very basic signals that we may transmit in a communication system. Today we'll continue investigating how the communication signals are designed. We saw yesterday that the basic sinusoid, a sine wave, and there are three parameters that impact upon the shape of that sine wave: the peak amplitude, which is a multiplier, which increases the amplitude; the frequency, which increases or changes the how often a cycle is repeated over time; and the phase, which visually we can look at as a shift of that sine wave relative to some origin point. And we said that in fact we can combine multiple sine waves, and this example is just adding two sine waves together using where each of them, the two different sinusoids, have different parameters, different peak amplitudes, different frequencies, but the same phase in this example. And by adding them together we get a different signal. And in theory we can create any communication signal that we want, a complex signal, by composing multiple sinusoids together. And looking at it from that perspective makes it easier for the designers to design the signals and to analyse them to make sure that they meet certain requirements. And we'll talk about the requirements today. I want to show you some signals, some real ones. The ones we're looking at, the sinusoids, are very basic. They're not real signals that we transmit. But it's not easy to capture a signal that's transmitted across the air, to look at the physical, the energy changing. So we cannot give a demonstration of a real communication signal. But I have some pictures, and you may have seen this. A spectrum analyzer. If you're doing the TC program, then maybe in a lab you see the spectrum analyzers, which on this screen shows some plot of a signal that's being captured, a real communication signal. We'll look at the structure of that plot shortly. You may have seen when you use Wi-Fi, for example. This is with Android or an iPhone, you can look at the signal strength of multiple access points nearby. So here's another plot which is showing, in fact, different frequencies or Wi-Fi channels and the signal strength in this axis. So the higher the plot is here, the stronger the signal. And normally, if your mobile phone or your tablet, you want to connect to the access point with a higher signal. So there are examples of signals. And here's just another one from this is a plot from a spectrum analyzer showing some wireless signal which was captured. So you need specific hardware to capture and to view the signals. All of the three that we've shown, these three examples, are shown in the frequency domain, not in the time domain. So we need to explain what the frequency domain is. But one example that we can give in the lecture, which is easy because I don't have the hardware, is our audio signal. So we record the audio and your computer captures that signal, or my computer has captured some signal. This is the audio from our lecture yesterday. So it's just recording audio and opening it in an audio editor, in this case Audacity. So this plots the signal, the audio signal in this case, as a function of time. So on this axis we see going from time 0 up to 1 hour and 15 minutes. And this is the signal strength. So S is the signal strength and T on the other axis is the time. We can zoom in and look at that because that's over a 1 hour period. Just looks like you cannot make much sense out of it. So if we can select some part and zoom in, we can see that the signal strength is changing over time. So a real signal in this case, an audio signal, but same concepts when we use digital and analog communications. If we keep zooming in on a specific part, and now we see it start to take some shape of, okay, something varying over time. So this is zoomed into, the scale here is, so this is 18 minutes, 23 seconds, 70 milliseconds. This is 80 milliseconds. So this period here is, or the period highlighted is about 20 milliseconds of audio. So we can see it's got this shape of some communication signal, in this case an audio communication signal. Varying over time, representing the noise that's being captured by the computer, the sound. We will use, just to demonstrate, I'll use audio signals today to demonstrate how we can combine sinusoids to create a more complex signal. Only using audio because I can show it on the computer, or generate it on the computer. So we'll come back to that in a moment. That was a plot of our signal in the time domain. It was the signal strength versus the time. We can represent a signal in the frequency domain, which is the peak signal strength versus the frequency. And the way to think about that is to think about the sinusoid components. In the first, or in the example we have here, we finished with yesterday, we have two components. It's the addition, the top equation is the addition of two components, where if we multiply out, we have 4 on pi sine 200 pi t, and the second component is 4 on 3 pi, because there's a multiplier by 1/3 here, sine 600 pi t, where the signal that is on the screen is the sum of those two, S1 of t plus S2 of t. And if we look at the individual components, we can identify the peak amplitude, 4 over pi for the first one, 4 over 3 pi for the second one. We can identify the frequency. The frequency, when we calculated yesterday, of the first component is 100 hertz, because remember the general structure is 2 pi ft, so f is 100 hertz. And the second component, f, is 300 hertz. And the phase in both of these is 0, just in this example. The peak amplitude, the phase is 0, and the frequency of the components. In this specific example, we note that the frequency of component 2 is in fact 3 times the frequency of component 1. Okay, 3 times 100. If we have such a structure where we have a signal where the sinusoid components have frequencies which are integer multiple of one of the others, then that one base one is called the fundamental frequency, and the other components are harmonic frequencies. So in this case, our fundamental frequency is 100 hertz. F subscript here means fundamental. And the frequency of this signal here, which is composed of the two S1 and S2, the frequency of S is the fundamental frequency, 100 hertz. That is, the frequency of S1 is 100 hertz, the frequency of S2 is 300 hertz, the frequency of S is 100 hertz, because the two components of this structure where we've 100 and 3 times 100. If we have that structure, then we can immediately determine the frequency of this signal. And of course, if we know the frequency, we can work out the period. It's just the inverse. Viewing it in the frequency domain, we apply a transform, a Fourier transform, and we're not going to cover the mathematics. We can convert these equations into showing from the perspective of not time, but of frequency. We're just going to look at the plots. On the next slide shows a plot of the signal in the time domain. In the frequency domain, we plot against the frequency, f, and the peak, so that's the uppercase F, S, the peak amplitude. And what we do is we look at the components inside this signal, look at the frequency of those components and the peak amplitude. So our signal S of t has two components, S1 and S2. S1 has a frequency of 100 hertz. So here's 100 hertz. And that component has a peak amplitude of 4 divided by pi, which is 1.3 something. 4 over pi. So what we get in a plot from the frequency domain is an impulse at that frequency and with a height of the peak amplitude. So it's a plot of the frequencies and their corresponding peak amplitudes. Whereas the plot in the time domain is a plot of the peak of the amplitude against time. And we have a second component which has a frequency of 300 hertz and a peak amplitude of 1/3 of 4 on pi. So in fact, it will be 1/3 of the height of this one, which is about here. Don't worry about the value of 4 over pi at the moment. Don't worry why we've introduced that. We'll see that shortly. It's just to plot a signal in the frequency domain, we look at the individual sinusoid components that make up that signal, and for each of those components we find its frequency and its peak amplitude and plot an impulse at that point. In our case, we have just two components. We have two impulses. This is the plot of our signal in the frequency domain, and in the next slide, the one down the bottom is the plot of the exact same signal but in the time domain. Amplitude versus time, peak amplitude versus, this is f, versus frequency. Same signal, just two different viewpoints of that signal. Just a mathematical transformation to go from the time domain to the frequency domain using Fourier analysis or Fourier transforms. Why do we do this? Well, we do it to make it easier for the people who the people who are designing and analysing the signals. Generally, consider the frequency domain much easier to consider to view the signal, to check whether the signal meets certain requirements, and we'll introduce those requirements, I think, in the next slide. When we analyse signals, we normally look at them in the frequency domain because we care about the frequencies that are used in that signal. So before we go back to that, a few more definitions. Well, here's the example. It's just a general example where it looks almost the same as this, except we don't use a specific frequency. And this, on the slides, and if we go back to the equation, in my example, we've used this equation where we had 200 pi, 600 pi t. we could substitute or replace this 200 with 2 pi f t. So the general form, 2 pi times by the frequency, here's we see 2 pi times 3 times the frequency. If f was 100, these two are exactly the same. It's just in the slides, rather than looking at a specific frequency, 100 hertz, the slides consider a general frequency, any frequency. F could be 100, 1000, 1,000,000, 463, whatever we like. We'd get the same shape plot, just on a different scale. And that's what these plots have. They don't give the exact value of f. And therefore the period is not known. But in terms of the shape, it's exactly the same. The first component, a sinusoid, the second component, add them together and we get the resulting signal, S of t, in the time domain and over here in the frequency domain. Here's another, this one's just an example of a signal in the frequency domain of a different signal, and in the time domain, S of t, from memory, it's a square wave. So if this is our signal in time domain, we have some level and then down to 0 for the rest of time, then in the frequency domain it looks like this. The point is that we don't always just have a single or a set of impulses here. It can be continuous in the frequency domain. And in practice they look like this. That is, it's in the frequency domain it's a continuous plot. Why use the frequency domain? It makes some concepts much easier. When we choose a technology for data transmission, some of the factors we care about are the frequencies which are used by the signal that we transmit. So let's introduce the notation or terminology to talk about the frequencies. The spectrum of a signal is a range of frequencies it contains. So the spectrum of, actually we have the answer over here, the spectrum of S1 is, it only contains one frequency component, is simply 100 hertz. Of S2 is 300 hertz. Of S of t here, we'd say the spectrum, it contains two frequency components. The spectrum is 100 and 300 hertz. So it's the range of frequency components that signal contains in it. Yeah? In this case, there's just two impulses, two frequency components. In a realistic case, like this one, there's a range, yes. So in the simple case I'm considering, there's just two components, 100 and 300. In more realistic cases, it has a range, an infinite set of values. But the spectrum is the range of frequency components. The absolute bandwidth of a signal is the width of that spectrum. That is the value of the maximum frequency minus the minimum frequency in the spectrum. And now let's just focus on S of t. I'll just say the absolute bandwidth, or sometimes just called the bandwidth, is 200 hertz. 300, it ranges from 100 up to 300. Therefore, the width is 200. We'll come to the DC component shortly. Looking at our plots, looking at this bottom plot, this is our plot of the signal. If I show you this, and I ask you, what's the bandwidth of that signal? How do you find it? What's the absolute bandwidth of the signal at the bottom? And some people asked me yesterday, okay, how do I draw this signal? Or how do I take this signal and find the frequency? Well, it's not easy. You need some computer to do that. That is, how do I, given this, can I break it back into these? Well, not easy. Similar, how do you plot this? Well, you use a calculator or a computer to plot it. The frequency information is not clearly shown in here. You need to do some analysis to find the frequency components from, given this signal, and to then work out the spectrum and the absolute bandwidth. Well, what about this plot? Same signal, but in a different domain, from a different perspective. If I give you this, you can immediately see the spectrum and absolute bandwidth of the signal. The spectrum, there are just two components at 100 and 300 hertz. The bandwidth is the difference between the two, 200 hertz. That's one of the reasons of using the frequency domain is easier for analysis of communication signals. Again, the same signal, just two different viewpoints of that signal. This one, we can see information about the frequencies much easier. And in most signals, the frequencies is what we care about. The frequencies and therefore the bandwidth and spectrum. What do you think the absolute bandwidth of this signal is? And it keeps going. What do you think the absolute bandwidth of that signal is? Well, it turns out it becomes infinite. That is, this sine wave, you can see it's high, or this waveform, and it's getting lower and lower and lower, but in theory it will keep going, getting smaller and smaller and smaller. In theory it has an infinite absolute bandwidth. And most signals that we deal with do have an infinite absolute bandwidth. The simple ones we consider here has a finite bandwidth, but in practice they look more like this. So most signals have an infinite absolute bandwidth, which is not so good. But in fact, most of the energy is contained within a small band. And that's what we normally call the bandwidth, the effective bandwidth. You can imagine it gets very, very small here. The peak amplitude is very, very small as we get past some point. Most of the energy, the highest points are here. Okay? So we can think that this signal, although it may have, in theory, an infinite absolute bandwidth, we could define some effective bandwidth and say, okay, the effective bandwidth finishes, it goes from here up to maybe here. And there are some different definitions of where do we cut off, or how small should the components be to ignore them, to treat them as zero. So the bandwidth that people talk about normally when they're dealing with real communication signals is in fact a practical limitation of, or takes the signal and assumes that some components are very, very small and we treat them as zero, and therefore we can calculate a real effective bandwidth. We'll see, and that's what becomes important for us as computer scientists, is that the bandwidth of a system and of a communication signal impacts upon the data rate, the number of bits per second we can send. And we'll go through some simple calculations to see the relationship. Okay, another definition, a signal contains if a signal has a component at a zero frequency that has a DC component. Here's an example. Same signal, we see the equation, it's 1 plus what we had before. We plot it, and we see the average over time is at 1. The difference here is that the middle point is 1, not 0. And in the frequency domain, we see at frequency 0, we have an impulse. We'd say this is the DC component. Normally, for practical reasons, when we implement transmission devices, we want to avoid DC components. We don't want to have signals such as that. So, we can take sinusoids, combine them together to get different signals. The signals that we want to produce to transmit across some communication system. We can view signals in the time domain, and here's an equation for a signal in the time domain. Here's a plot for a signal in the time domain. But we can also transform it into the frequency domain, that is, as a function of frequency. And here's a plot of the same signal in the frequency domain. For designing and analysing signals, the frequency domain is commonly used. And the examples that I showed at the start of the lecture, here's one example, a capture of some signal in the frequency domain. On this axis, we have different frequencies. Some centre point frequency, which I think is, say, in the middle is 1 gigahertz, and it spans 11 megahertz. So slightly less than 1 gigahertz is at this point, and slightly larger than 1 gigahertz. And we see there's not just impulses like our simple case, there's a continuous range of frequency components. But we see most of the energy because this axis shows us the peak signal strength. Ignore the units, but we see, okay, the signal is strongest with these within this frequency range, within this spectrum. And in fact, very weak in this area. So we could consider the bandwidth of this signal ranges from this point up to this point. So this is a capture of a real signal that was transmitted across some wireless link. Spectrum analyzers, the previous pictures, show, again, you cannot see it clearly, but show signals in the frequency domain, because that's what we care about mostly, the frequency components in the signal. What about our voice? This audio software shows our signal in the time domain, but it in fact can analyse and convert it to the frequency domain. And there are some algorithms to apply on the time domain values to get a plot in the frequency domain. So the software will do it for us. Plot the spectrum of this signal. That is, plot the signal in the frequency domain. And here it is. What we see, signal strength. Again, don't worry too much about the units right now, but the higher it is, the higher the signal strength, and the frequency. So for that 1 hour of audio, they are the range of frequencies. I can highlight the highest point here. So the strongest component in this case is at frequency, it tells me, of 789 hertz. Okay? Across that 1 hour of audio, it contains multiple frequency components, this signal. The strongest is at 789 hertz. And then the next strongest, we see that next peak, is at 1,300 hertz. And we can see that most of the signal strength is in this range, which is from 0 hertz up to what? Maybe about 4,000 hertz, 4 kilohertz. 1,000, 3,000, 5,000 here. And then it goes out with much weaker signal strength to up to 20,000 hertz, 20 kilohertz. This may be a little bit deceiving because it's a logarithmic scale here. The way to interpret it is that every line is a reduction of 1/2. If this is the maximum signal strength, at this point it's half as strong as the maximum. And at this point, this is 1/4 the strength of the maximum. So down here it's very, very weak, even though it may look reasonable, but it's much, much smaller than the maximum. So most of the signal energy is in the first several thousand hertz in this case. Which makes sense because when people talk, they normally talk in the range of frequencies up to around 4,000 hertz. All right, maybe some higher frequencies, but speech typically ranges of 0 up to 4,000 or 5,000 hertz. So we can view a signal in the time domain and the frequency domain. This is the audio, and if I want to transmit that audio across some communication system, e.g. a telephone line, okay, say that's the audio that the person creates, and then they have their fixed telephone and they want to talk to someone, then the data that's created has frequencies in this range, so very strong for the first few thousand hertz and then very weak for the up to about 20,000 hertz. A communication system, depending upon the media, will support specific bandwidth of frequencies. For example, the telephone line, the fixed landline telephone, as an example, supports transmission of a bandwidth of 4 kilohertz. 0 to 4,000 hertz. So when you talk on the fixed telephone, even if you talk at a very high frequency, above 4,000 hertz, the telephone line will only transmit the frequencies from 0 up to 4,000 hertz, which covers most people's voice, but very high frequencies will not be captured. They will not be transmitted across the telephone line. So communication systems have limits on the range of frequencies in which they transmit. And we'll look at some more examples of those shortly. Let's go back. So we have signals made up of sinusoids in the very basic form. Each sinusoid has some frequency. If we have the structure of the signal where the components have frequencies which are integer multiples of one of them, 100, 3 times 100, then the resulting signal has some common structure where the fundamental frequency is the base frequency of that component. We have spectrum, which is the range of frequencies in a signal. We have absolute bandwidth, which is the difference between the maximum frequency component and the minimum, and effective bandwidth, in that in practice, if we have infinite absolute bandwidth, we may limit that to a real, a practical value. And we've said that the bandwidth determines the data rate. Let's try and explain or give a demonstration of how that relationship comes about. On these two slides we have some plots of signals, but I'll do it on the computer to show a different example. Let's close this one. The top plot is the plot of our signal with 2 components. Okay. The bottom plot here is the plot with 3 components. We see it's slightly different, similar shape. In the next slide, this plot has 4 components. We'll look at the equation shortly. And in the bottom plot, we have an infinite number of components, which leads to a square wave or a digital waveform. Now let's imagine now we want to transmit bits. We can use these signals, if we can transmit these signals across a link, we could use them to represent zeros and ones. One obvious way would be if the signal is high, it represents bit 1, and if it's low, it represents bit 0. Looking at the bottom one here, over this time period, how many bits could we transmit? How many? 4 bits. So we could say that this signal represents a sequence of 1010. 4 bits. If I wanted to transmit the bits 1010 from my computer to another, I could generate a signal which looks like this. Where effectively what it does for some time period, we have a signal strength, a high signal strength, and then for bit 0 we have a low signal strength for the same time period. Alternatively, we could use the signal above it, in that it approximates this square wave. You can see the shape is very similar. It approximates the square wave. So we could say that, okay, this high, it's not always at 1, it's very close to 1. For that period of time, that represents a high value, or bit 1. And when we're low, close to -1, it represents a low value, a bit 0. So alternatively to using this signal, we could use this signal to transmit our 4 bits. Or one of these 2 signals. So the communications designer, the one who has to design the transmitting devices, needs to now choose one of these signals, or one of many signals to transmit, to represent the data. Let's say in our case we have 4 choices, the 4 different signals shown in these plots. Of course we have many more. Let's try and look at the relationship between the frequency of the signal, the bandwidth, and the data rate, the number of bits per second. Let's make some space so we can calculate. You can see in all of these, if you can see the equation on your slides, they all have this multiplier of 4 over pi. Where does that come from? That is just introduced to make the pictures look nice. By nice, I mean to make them all be close to 1 at the top, or -1. Remember, a multiplier, or the amplitude, just increases the height of the signal. So this 4 over pi is introduced so that we get the average strength as 1.0 here. If it wasn't there, then the shape would be the same, except it would be a bit lower here and a bit lower here, or different position. So that's not so important. Let's write down the signals. Going back to our original equation. In this example that I go through, in the original example we had 100 Hertz as the fundamental frequency. Let's change it to 1000 Hertz because it'll be easier on the computer. That is, we have a signal which is, I'm not going to write the 4 over pi, but sine 2000 pi t plus 1/3 sine 6000 pi t. And just for reference, let's do it over here. Our general equation for our signal A sine 2 pi ft plus the phase. In the examples, we're going to have a zero phase. We are going to focus on the frequency. The amplitude, we'll see there's some structure. We could multiply here if we want. Here's our first signal. The only difference is that I've multiplied the frequencies by 10. Instead of 200, 2,000 and 6,000. So the frequency of the first component is 1,000 hertz. And of the second component is 3,000 hertz. Three kilohertz. Because if you follow the general equation, it's 2 pi ft. So f must be 1,000 hertz. And the fundamental frequency is, or the frequency of our signal, SA, the fundamental frequency is 1,000 hertz, as is the frequency of our signal. Because we see it has this structure of 1,000 3 times 1,000. We've designed it in that way, or have chosen it in that way. We could say of this signal, the fundamental frequency, f, lowercase subscript f, is 1,000 hertz. Because all of the components are a multiple, integer multiple of 1,000. 1 times 1,000, 3 times 1,000. What's the period of signal A? What's the period of signal A? You can look at the plot and to work it out, or you can simply calculate it from the information on the board. What's the period of signal A? 10 to the power of minus 3 seconds. The frequency of this signal is in fact the fundamental frequency. So I could say the frequency of signal A is 1,000 hertz as well. And the period is the inverse. 1 divided by 1,000 seconds, 1 millisecond in this case. I'm going to try and plot these signals on the screen. You can use some mathematics software to plot them, a calculator, MATLAB, or some other plotting software. But I don't have that, so I'm just going to create the audio signals and use our audio analyzer to plot them. And on my computer, I have some audio software that creates signals for me. It's called SOX. It's just a program that will create a signal, an audio signal in this case. What it actually does is converts one audio file to another. But in this case, I'll use it to create my own audio file. What do we want to create? As an example, first let's create a 1,000 hertz sine wave. This is just audio processing software, and it creates, I'm going to create a WAV file. You all know WAV file as an audio format. It's a raw format for storing audio. And I'm going to create this example 1,000 hertz WAV file. And because I want to create audio, I need a synthesizer. I need to tell it to use a synthesizer and create audio for 1 second, just 1 second, 1.0 seconds, and create audio that simply follows a sine wave. And the frequency, 1,000 hertz. It's just a software to create some audio file. It creates it, and I will load that file in so I can see it. Okay, doesn't look very useful, but if we zoom in, okay, so there's our audio file. And you see, if you look at the time scale, the period of the signal should be 1 millisecond. If I can highlight, over that period of time we see that from 0.02 up to 0.03 seconds, that is 1 millisecond, we have one iteration of the sine wave. So there's our first component, our 100 Hertz sine wave. I can go back and create a second component, this time our 3000 Hertz sine wave, different file. And then, again with audio processing, you can take two different audio files and mix them together, basically add them together. And that's what we do in our equation. We take two sine waves and add them together. But note there's one thing different. It's the second component has a peak amplitude which is 1/3 of the first component. So if we say the peak amplitude here is 1, this one is 1/3. So when we mix them together, we need to reduce the peak amplitude of the second component. And I can use SOX also to mix them together, if I can remember how. Combine them, or mix them. And I specify the file that I want to mix, the example 1000 Hertz file. And actually, and then because we want to specify a magnitude in the audio, the magnitude is the volume. So the first one I'll set a volume of 1.0. That's the first component, has a magnitude of 1, or a volume of 1 in terms of audio. The second component has a volume of 1/3, let's say 0.33. And then the file name. And produce some output file. It's just going to add those two input files together, but the volume specifies, okay, set the magnitude of the first one at 1 and set the magnitude of the second file at 1/3, and then add them together, which is this equation, and produce the result in the example with two components. And now let's open them and look at them. I've already got the 1000 Hertz file opened. Let's open the other two. Open 3000. So they're the two components, 1000 and 3000 Hertz. We'll zoom in a moment. And the mixed file, example 2. And now zoom in. Okay, so we see, as we see in our slides, adding these two files together, reducing the height of this one. Here it's plotted as a height 1, but when we set the volume, we reduce it to a height of 1/3. Then adding the two together, this is the result. You can do this in any mathematics software as well. This is a signal which we're going to use to transmit our data, and this one has two components. We could add another component, a third component, and we'd get, if we go back to the slides, we get a similar signal but slightly closer to a flat digital waveform. I've done the calculations before, so I won't do all those again. I'll load up the ones that I've calculated earlier. First, any questions? All I've done is trying to show you the plots by adding two sine waves together. Yep. How to get frequency A? Okay, the question, it's a good question, is, okay, we know the component frequencies, 1 and 2. If signal A is made up of the components where the component signals are integer multiple of 1, which it is. That is, if we have a fundamental frequency, then the frequency of A is the fundamental frequency. So it's the same in this case. So it's 1000 hertz. And hence, the period of A is also 1 millisecond. And we see that here. Signal A, which is the bottom plot, if we highlight for some period of time, the time frame here, this signal has a period of 1 millisecond. This has a period of 1/3 of a millisecond. The resulting signal has a period of 1 millisecond, about here, because the frequency is 1000 hertz. FA is in fact FF, the fundamental frequency. FA is the frequency of signal A. Because when I draw some other signals, we'll call them B, C, and D. That's all. So it's the frequency of our signal A, i.e. the frequency of this bottom plot. I'm going to close the top two and look at the spectrum. Okay, we see our two components. The way that the analysis is done, see, it's not perfect, it's not an impulse, but it highlights the frequency components. The first component, if I leave my mouse there, has a peak at around 1000 hertz. The second component has a peak at 3000 hertz, slightly lower. It's in fact, remember this is a logarithmic scale, it turns out it's 1/3 of the first one, which is our plot here, effectively, except on a different scale. Let's leave our plot up there. How many bits per second can we send with this signal? If we say that for some period of time, when the signal is high, it represents bit 1, and when the signal is low, it represents bit 0. How many bits per second can we send with our signal A? What's the data rate we could achieve? Calculate the data rate. Looking at the signal, think, okay, if we use the high to represent 1 bit and low to another bit, how many bits per second could we send? I'll highlight that portion. If we look at the scale, this is from 0.002 seconds to 0.003 seconds. That is, that's a period of 1 millisecond. How many bits in there? 2 bits. We see we have a high level and then a low. So 2 bits in 1 millisecond. That is 2 bits per period. That is, if you have a sine wave, you've got a high portion and a low portion. So 2 bits within the period. Therefore, in 1 second, and you could count them if you wanted to, 2000 bits. So the data rate we can achieve with this signal is 2000 bits per second. Let's make note over here. We could achieve a data rate of 2000 bits per second with this signal. What's the bandwidth of our signal? What's the bandwidth of the signal? 2000 hertz. Let's make note of that. Remember, when we see the plot, or simply it's the difference between the maximum frequency component and the minimum. 3000 minus 1000. The bandwidth of signal A is 2000 hertz, 2 kilohertz. And the fundamental frequency, or the frequency of A, was 1000 hertz. So if we use this signal, which is made up of just 2 sinusoids, then we will use or occupy a bandwidth of 2000 hertz, and we could achieve a data rate of 2000 bits per second, 2 kilobits per second. When we design a signal to transmit, we need to consider these factors. The limitations will be, normally we have a fixed bandwidth to use. That is, you need to design a signal that fits within some bandwidth. And you want to get the highest data rate as possible. In this case, if we use a bandwidth of 2 kilohertz, we get a data rate of 2000 bits per second, 2 kilobits per second. What if we change our equation or change our signal? Let's do it over the other side. That can stay. What if we change the values so that signal B was what do we want? What if we used a different signal, signal B? What are the characteristics of that? What's the question? Ask, it's okay. We have time. Okay, if no question, what's the bandwidth of signal B? Let's start simpler. What's the frequency of the first component in signal B? There are 2 components. What's the frequency of the first component? 2000. 2000 hertz. 2 pi ft, we have 4000 pi t, we get 2000 hertz. Second component, frequency, 6000 hertz. Bandwidth of B, it's 6000 minus 2000, it's 4000 hertz. Frequency of B, or the fundamental frequency of B, is 2000, because we see it's 2000 here, or 1 times 2000, 3 times 2000. They're both integer multiples of 2000. This is 1 and this is 3. So the frequency of B, or the fundamental frequency, is 2000 hertz. Data rate, if we use signal B, or it's simpler, first, period of signal B. No, this period of signal B. Half a millisecond, 0.5 milliseconds. That is, it's 1 divided by 2000. Here we have 1 divided by 1000, we get 1 millisecond. Here we divide it by 2000, we'll get half a millisecond. Now the rate, the data rate, using signal B. Look at what we did over there. We looked at 1 period, and we see that we can transmit 2 bits in 1 period. So how many bits per second? We've got, although we don't have a plot of this signal, it will still look like this, where we'd have, it's just on a different time frame. 1 period, we can transmit 2 bits. 2 bits in half a millisecond. Therefore, 4 bits in 1 millisecond, 4,000 bits in 1 second. Four bits in 1 millisecond, 4,000 bits in 1 second. 2 different signals now, signal A and signal B. I'm not going to plot it, but if we plotted signal B, we'd get the same shape, just on a different time scale, because it has a different frequency. But we'd still see these two humps here at the top and down the bottom. With a different, well, what can we see by comparing the two? Focus on the data rate, the bandwidth, and the frequency. Same shaped signal, increasing the bandwidth from 2,000 to 4,000 increased our data rate. We've doubled the bandwidth from A to B, and as a result, doubled the data rate. So we're seeing the relationship between frequency, bandwidth, and data rate. Any questions on our calculations before we look at these relationships? Everyone's okay? They can calculate this in the next quiz. Given a signal equation, or even a plot in the frequency domain, calculate the data rate. Okay, so one point to notice is that we see the data rate on the signal A is 2,000 bits per second, the bandwidth is 2,000 hertz. And in B it's 4,000, 4,000. Are they always the same? No. No. Just a coincidence in this case. So the data rate is not always the same as the bandwidth. It is in these two, but we'll see another example where it's not. Okay. Any other questions? The assumption we're making is that the high point we can transmit 1 bit and the low point represents another bit. Increasing the bandwidth from 2,000 hertz to 4,000 hertz increases our data rate, doubles our data rate. That's good. Normally we want high data rate. Okay? We want a signal where we can send the data as fast as possible. We know that if we increase our bandwidth, we can increase our data rate.
If you just use a sine wave, doesn't it read 1, 0, 1, 0 the whole time?
Then, and the question is, what if we just use a sine wave? What if we use a different signal? I'll try and answer that by not using a sine wave, but the same principle, but using a sine wave is one component. Okay? A sine wave is one component. We've used a signal with 2 components. Let's do another calculation with a signal with 3 components, and we'll answer that question then, of why not just use a sine wave. I'll use 3 components because it looks a bit better. I have a plot of using 3 components, which I did before. I'll open that just to show you. I hope I do. Our signal using 3 components. Zoom in. The top one is using 2 components, the bottom one using 3 components. Okay. We'll write the equation in a moment. What's the difference? Well, one is, what would you say about the second one? Think about our pure digital waveform, the one which is square. Which one's closer, the top or the bottom? The bottom one is closer. And we'll talk shortly why that's significant. Getting closer to the pure digital waveform, we'll see, gives us better accuracy in our signal, less chance of errors, which we haven't mentioned yet, but we will shortly. Generally, we want a closer one to the digital signal. Let's do the calculation for this new signal, signal C. Where will we do it? Here. How did I generate that signal? It's these two components plus a third component. Sine 2000 pi t plus 1/3 sine 6000 pi t plus, and let's remove this, plus a third component. And the structure that I've used, and you'll see it in the equations, 1/5 sine, what have we got? 10,000 pi t. Same as the signal A, except this third component is 1/5 sine 10,000 pi t. Frequency of the first component. Frequency of this component. 1,000, same as before. Second component. 3,000, that's the same as before in signal A. Last component. 5,000. You see the pattern happening there. In general, 103, 3 times 1,000. Fundamental frequency, this is 1 times 1,000, 3 times 1,000, 5 times 1,000. Our signal frequency is going to be still 1,000. The frequency of C is still 1,000. Same as the frequency of A. Bandwidth. Bandwidth of our signal. 4,000 now. Maximum component 5,000. Minimum 1,000. The spectrum is 1, 3 and 5,000. The bandwidth from minimum to maximum, the difference is 4,000. Data rate. So remember the definition of the absolute bandwidth is the difference between the minimum frequency component and the maximum. We've got 1, 3 and 5,000, so it's 5,000 minus 1,000. And the data rate of signal C, what's our data rate? Do the calculation the same as we did over there. Again, here's our signal, in fact. It's this signal here that we're calculating for. If we highlight this period, we can transmit 2 bits in a time frame of 1 millisecond. It's the same as our first signal. It's the same as A. Note the frequency is the same. That is, therefore the period is the same. Therefore the number of bits we can transmit in a period gives us the same data rate as A. Now, see the difference between our three signals, A, B and C. Comparing A and C. Same frequency, 1000 Hertz. To go from A to C, we've doubled the bandwidth, but we haven't increased the data rate. Still 2000 bits per second. So we use more bandwidth, but we get the same data rate. The benefit of using signal C compared to A is that we say it's more accurate. There's less chance of errors when we transmit this signal, that the receiver will have errors. That's not something we can put down in numbers here, saying it's more accurate. For now, and we'll give some more examples later, but for now, the closer the signal is to our pure digital waveform, the more accurate it will be to transmit data, the less errors which will occur in the transmission. So comparing these two, if we want to get more accuracy, we use signal C. Less errors, signal C compared to A. We get the same data rate, but the problem with signal C is we use a higher bandwidth. And it turns out that we want to use as small bandwidth as possible because other people want to use that bandwidth, and in fact, the more bandwidth you use, the more it costs. So what we want to do is minimize the bandwidth, maximize the data rate, and maximize the accuracy, or minimize the chance of errors. Compared to A to B, A and B have the same shape, the same accuracy. But from A to B, we increased our frequency and bandwidth from 2000 Hertz up to 4000 Hertz for our bandwidth. Increasing the bandwidth gave us higher data rate, comparing A to B. Higher bandwidth generally leads to higher data rate. The signal that we choose will impact upon the accuracy of our transmission. So we need to choose a signal which has high accuracy, low bandwidth, high data rate. And there are three competing requirements. And of course, there's no one optimal answer. I'll open one more signal which I created earlier. So we had two components, three components. I created one with 100 components. Okay. So 2 components, 3 components, 100 components. Zoom in. There's our much more accurate signal. Just combining 100 sine waves together using this pattern. 1/7 sine 7 times 2000, 1/9, 1/11, and so on, up to 100 components, and we get almost a perfect square wave here. If you add an infinite number of components, it will be the perfect square wave, in theory. This 100 component signal gives us the same data rate. They all give the same data rate of 2000 bits per second, all three signals. This 100 component signal uses a much higher bandwidth. That's the problem. The top signal uses 2000 Hertz, 4000 Hertz. What is it? 100. I can't calculate what the exact bandwidth is. I think it's almost 100 times what we have here, 2000. So it's much higher bandwidth used. So the advantage of the bottom signal is it's more accurate, less chance of errors. We cannot put numbers to that right now, but we say that there's less chance of errors in this signal than the other two. Yep.
What's the disadvantage of high bandwidth?
The disadvantage of high bandwidth is that, and we'll see in the next topic, that the spectrum, the range of bandwidth we have available is limited. Okay? And it turns out that you need a license for a bandwidth, otherwise or for most bandwidths. So one company wants to use the same bandwidth as you, so you only have a limited portion available to you. Basically, the more bandwidth you use, the higher it costs financially to use those frequencies. We'll cover that when we talk about transmission media, but high bandwidth costs more. It's generally harder to create the devices that transmit and receive at those high bandwidths as well.
Will the sine wave always transfer 1, 0, 1, 0?
And then, okay, we're saying we transmit 1, 0, 1, 0, 1, 0. We don't want to do that always. We want to transmit a different sequence of bits. So how do we do that? If we want to transmit a sequence of bits, which is some random sequence, one simple thing we can do is use this signal, but when we want to transmit a bit of a different sign, is change the phase of the signal. Remember, the phase of our signal does a shift in the signal. The phase shifts the signal along. If we shift the phase by pi, here we go up at the start. If we shift it a bit more, we'd go down at the start. By using a different phase, we'd get either the signal immediately going up to the high point to represent a bit 1 if we want to transmit it. If we want to transmit a bit 0, we'd use the opposite phase and transmit down low at that point. So our transmitter changes the phase as we have different bits. That's just one example of how we can do it. So we don't transmit this all the time. If I want a bit 1 to transmit, I use the 0 phase. Then my transmitter, when I know I have a 0 to send, I change the phase so that I send the low signal. That's one example of how to do it. So this is just a way to calculate the data rate. Of course, we do not send signals like this because we have different sequences of bits to send. But still the same approach in calculating the data rate. Tomorrow we'll do nothing. Next week we will summarise and look at the different types of analog and digital data. Just move through to the last slide, I think, just to check that we've almost finished. They were the ones that I showed, or similar. This is a calculation which we did on the board, but we used different values. We'll summarise with a relationship or trade-offs between bandwidth, data rate and accuracy next week and move on. Enough for today. You don't have to know how I generated those audio signals. They were just for the